Everyone. Myself Lakshmi Prasanna, working as assistant professor in Department of Soil Science and Agriculture Chemistry, SR University, Warangal, Telangana. Today, as part of our soil science course, Management of Problem Soils and Irrigation Water, I'm going to discuss about the quality of irrigation water. So I want to give a brief introduction about the quality of irrigation water. Almost all natural waters which are used for the irrigation purpose contains both organic salts and also inorganic salts in the solutions, which are derived from basically from the rocks or solid parent material through which this water percolates. The most common dissolved salts such as chlorides, sulfates, bicarbonates of calcium and magnesium. The sodium and proportion of these salts determine the suitability of water which is used for the irrigation. Other constituents such as boron, lithium, fluoride and other ions which are present in excessive amounts may also have the toxic effect on plants and also occur in the lesser amounts in the irrigation water. If this water is used for the irrigation purpose containing excess quantities of these particular nutrients, it may also have the growth of the plants is severely affected in three ways, like as the adverse changes in physiological characteristics of soil. Increased osmotic pressure of the soil solution may decrease the physiological availability of moisture to the plants. Accumulation of certain ions in the soil solution increases the concentration of that particular ions in the solution, thereby causing the specific toxic effect which causes the physiological deficiencies in the plants. All the natural waters which are used for the irrigation purpose contains the organic salts and inorganic salts. So these organic salts and inorganic salts, these salts are generally derived from the withering of rocks and minerals and also from the parent material, which is through which this water percolates. The most common dissolved nutrients like chloride, sulfates of carbonates and bicarbonates of calcium, magnesium, and sodium are the major salts present in this saline water. The concentration and proportion of these salts determines the suitability of water for the irrigation purpose. The other nutrients like boron, lithium, fluoride, and other ions which have the toxic effect on the plants, which occur in lesser amounts in the irrigation water. If these water which containing the above ions are excessive in quantities, then they may show the effect on the plants like adverse effect or the adverse changes in the physical characteristics of soil like wilting symptom, necrosis, death of the plant, chlorosis, increased osmotic pressure. So due to the increase in salts like chloride, sulfates of calcium, magnesium, and sodium, when there is increased amount of salts, there is osmotic pressure is created between the roots, between the plant roots and the soil solution. When more amount of osmotic pressure is created, the roots have to spend extra energy in order to obtain the nutrients from the deeper layers of soil, thereby creating the pressure. Because of that excessive pressure, it also causes the physiological drought condition. That means the amount of moisture will be available, but plants cannot obtain that particular moisture because of the semi-permeable membrane present due to the osmotic pressure in the saline soils. And also it also created the specific toxic effect. Specific ion effect is also seen when there is more amount of salts present in it. Specific ion effect is in the sense when the concentration of one ion increases, there is decreased availability of the other ion. Suppose like the concentration of the phosphorus ion increases in the soil, there is reduced availability of zinc to the plants. So in this manner, if the concentration of one ion increases, the availability of the other ions decreases. That is known as the specific toxic ion effect or specific ion effect, which is seen in the water where there is more amount of salts present in them. Criteria for evaluating the irrigation water. So first criteria is it includes salinity, sodicity, and element toxicities. So first is the salinity hazard. Salinity hazard, it is formed in the saline soils because of the excessive usage of saline water which is used for the irrigation purpose. On the basis of this, electrical conductivity measurement is done. So in order to determine the salinity hazard, electrical conductivity measurement should be done for the criteria for the irrigation water. So the classes in the salinity hazard includes low salinity, medium salinity, high salinity, very high salinity. So low salinity class is symbolized as C1, having the electrical conductivity 0 to 0.25 decisiemens per meter, having the salt concentration less than 0.16%. And it can be used, this low salinity water can be safely used for all types of crops and also used for the irrigation purpose in all types of soils. Medium salinity water containing the symbol which is denoted with the symbol C2, having the electrical conductivity 0.25 to 0.75, salt concentration 0.16 to 0.5%. This medium saline water can be used for the irrigation purpose by doing moderate leaching phenomena. Moderate salt tolerant crops can be grown in this by using this medium salinity water. High salinity water is designated as C3, having the electrical conductivity 0.75 to 2.25 and the salt concentration 0.5 to 1.5%. So in this high saline water it cannot be used where there is a drainage problem. So whenever there is a drainage problem, this particular high saline water cannot be used in that particular area. Salt tolerant crops and additional management practices should be followed. I mean salt tolerant varieties and also management practices like permeability, infiltration rate and drainage should be properly done in order to use this high salinity water for the irrigation purpose. Very high salinity, it is designated with C4, having the electrical conductivity 2.25 to 5 and the salt concentration 1.5 to 3%. This very high saline water cannot be used for the irrigation purpose because of the more concentration of salts present in them. It can be used occasionally by doing the leaching phenomena. Only the salt tolerant crops can be grown by using certain management practices. So here salinity hazard is one of the criteria for the irrigation water. So salinity hazard is mainly related with the high salt concentration which is present in the saline soil, and it is determined by using the electrical conductivity. Electrical conductivity measurements is done by 4 classes which is denoted by United States Soil Salinity Laboratory. Next is the sodium hazard. Sodium hazard is, this hazard is caused when there is high concentration or high amount of sodium which is present in the on the surface of colloids or in the soil solution. High concentration of sodium is undesirable in water because sodium absorbs the sodium which is absorbed on the soil exchange sites causes soil aggregates to break down. That is known as the deflocculation. Deflocculation leads to the sealing of the pores of soil, making the layer impermeable for the flow of water. The tendency of sodium to increase its proportion on the cation exchange sites at the expense of other types of cations is estimated by the ratio, sodium adsorption ratio. That is it is relation between the content of calcium plus magnesium in the irrigation water. It is known as the sodium adsorption ratio. So this sodium hazard is designated with the class that is the low sodium hazard, which is symbolized with S1, and the SAR value is 0 to 10. And low sodium hazard, it can be used for all soils with little amount of danger will be there. Medium sodium hazard having the symbol S2, having the SAR value 10 to 18. In this, the sodium hazard is likely seen in the fine textured soil and can be used on soils having the high permeability. High sodium hazard or high sodium water it is designated with the symbol S3 having the SAR value 18 to 26. It requires So for using this high sodium water, so it requires special management practices like good drainage water, high leaching, and addition of organic matter and gypsum can be done for the better utilization of this high sodium containing water. Very high sodium containing water having is designated with S4, having the SAR value greater than 26. This water cannot be used for the irrigation except at low temperature ranges, low temperature to the medium salinity irrigation water. Special management practices should be done like addition of organic matter and gypsum and growing of green manure crops for the usage of this high sodium containing water. So here in the sodium hazard is nothing but the hazard which is formed containing the soil solution containing high amount of water, high amount of sodium, which is present on the exchange sites of clay and also on the present on the clay colloids. So as the sodium is present in excess amounts, this causes breakdown. The soil particles seems to be breakdown because of the sodium. Sodium is loosely held on the surface of the soil colloids and also on the clay particle. Because of the presence of the sodium on the soil colloids, there is formation of the dispersion phenomena is caused. Dispersion or the deflocculation. Deflocculation is nothing but the particles, all the clay particles will move away from each other. That is known as the deflocculation or dispersion phenomena. Due to the deflocculation or dispersion phenomena, it leads to the sealing of the pores. Almost all the particles, all the soil particles all the clay particles are sealed. When clay particles are sealed, there is no proper drainage. There is no proper drainage and also infiltration rate is very low in this particular soil, which causes impermeable flow of water. So this sodium hazard is characterized by the parameter sodium adsorption ratio. It is estimated by the ratio of sodium content of calcium plus magnesium in the irrigation water. So sodium adsorption ratio is one of the criteria used in determination of sodium hazard. So SAR is nothing but it is determined by the ratio of sodium content of calcium plus magnesium in the irrigation water. So this is known as the sodium hazard. This diagram depicts the relationship between the electrical conductivity and the sodium hazard. So this is the electrical conductivity classes C1, C2, C3 and C4. C1 class is low saline, medium saline, high saline and very saline. This is the sodium adsorption ratio or sodium hazard having S1, S2, S3, S4. S1 is the low sodium, medium sodium, high sodium and very high sodium. That is the SAR value. So C1, S1 is very good. C2, S1 is very good, having the C3, S1 is a medium in nature, and C4, S1 is very bad in nature. I mean, this particular water cannot be used for the irrigation purpose, or if it is used for the irrigation purpose, special management practices like leaching, proper drainage and infiltration rate should be done in a proper manner in order to use this particular electrical conductivity of the high sodium containing water. Next is the salt index. Salt index is generally used for predicting the sodium hazard. It is a relationship between the sodium, calcium and calcium carbonate present in the irrigation water. Salt index is, the formula of salt index is total sodium minus 24.5 minus total calcium minus calcium in calcium carbonate into 4.85. Here the salt index is determined as the negative value, that is minus 24.5 to 0 for the irrigation water of high quality, and positive value of salt index is harmful to the irrigation crops. So generally the salt index is used for the predicting the sodium hazard, which is one of the criteria used for the irrigation water. It determines the relationship between the sodium, calcium and calcium carbonate present in the irrigation water. So generally, the salt index is usually negative for the negative. If the salt index is negative, that is minus 24.5 to 0 range, it is a good quality of water and having the high quality of water, and it can be used for the irrigation water. The salt index is positive, then it is not suitable for the irrigation purpose and it is more harmful to the crops. Next is the bicarbonate hazard. Bicarbonate hazard is nothing but the hazard which is caused or which is formed when there is more amount of bicarbonate ions present in the irrigation water. So the carbonate ions which are present in water, but bicarbonate may also be present. That means the presence of carbonates and bicarbonates, when it is present in more amount in the irrigation water, there leads to the formation of bicarbonate hazard. Based on the theory of precipitation of calcium and magnesium, Eaton in the year 1950 suggested the concept known as residual sodium carbonate, so which is commonly known as RSC. So the formula of RSC or the relationship between RSC is carbonate plus bicarbonate minus calcium plus magnesium. So a bicarbonate hazard is nothing but the presence of carbonates plus bicarbonates present in the irrigation water, which leads to the formation of the bicarbonate hazard. So the concept based on the precipitation of calcium and magnesium concept, Eaton in the year 1950 suggested the concept known as or determined the concept known as the residual sodium carbonate. So it is determines the relationship between the carbonates plus bicarbonates minus calcium plus magnesium. The range of RSC, which is measured in milliequivalent per liter, if the RSC value is less than 1.25, then it is most safely used for the irrigation purpose. If the RSC range is 1.25 to 2.5, it can be used for the irrigation purpose by doing certain management practices like gypsum application. If the value of RSC is more than 2.5, it is not suitable for the irrigation purpose. Here, for JRF point of view, here the important point is that the salt index value is negative, then that particular water is good and it can be used for the irrigation purpose. The salt index value is positive, then it is harmful for the irrigation. Next is the bicarbonate hazard. So bicarbonate hazard is determined with the concept known as the RSC, residual sodium carbonate. So the formula of residual carbonate, that is carbonates plus bicarbonates minus calcium plus magnesium, and also the RSC value, that is 1.25 range, is most safe for the irrigation purpose. If the RSC value is more greater than 2.5, then it is not suitable for the irrigation purpose. So this is the important point regarding the JRF point of view. Next criteria is the boron hazard. Boron is very toxic to the plants at very low concentration in the soil solution. Because boron tends to accumulate in the soil even at low concentration in the irrigation water, it is necessary to consider this constituent in assessing the quality of irrigation water. The USDA has suggested the type of crops to be grown with respect to boron in boron content in the irrigation water. So the limits of boron hazard includes 0.3 to 1. So boron concentration at 0.3 to 1 ppm. Then it is sensitive. It is sensitive crops. The crops can be grown like citrus, apricot, peach, apple, pear, and plum can be grown at this particular range. If the boron concentration in irrigation water is 1 to 2, then the semi-tolerant crops can be grown. Semi-tolerant crops includes sweet potato, oats, sorghum, maize, wheat, barley, radish, peas, tomato, cotton, potato, and sunflower. The boron concentration is 2 to 4. Tolerant crops like carrot, cabbage, onion, beans, sugar beet, alfalfa, and date palms can be grown at this particular concentration. Here, the boron is very toxic to plants at very low concentration in the soil solution. Because boron tends to accumulate in the soil solution even at very low concentration in the irrigation water. In order to assess this quality of irrigation water regarding the boron, USDA has suggested the limit for the boron concentration, which are described just now. So the boron tolerant crops, boron sensitive crops include the citrus, apricot, peach, apple, pear, and plum. Boron tolerant crops includes alfalfa, dates, beans, sugar beet. So these are the important points of view as per the JRF. Next criteria is the chloride contents. So the chloride ion generally have no effect on the physical properties of soil, and it is not absorbed on the soil complex. So it has generally not been included in the modern classification system. However, it can be used as a factor in certain regional waters classification, like so chloride, which is designated in milliequivalent per liter, is the ratio of chloride plus nitrate by carbonates plus bicarbonates plus sulfate plus chloride plus nitrate. So the chloride concentration includes, if the chloride concentration is 0 to 4, then it is excellent in nature. If the chloride concentration is 4 to 7, then it is good. The permissible limit is good. If it is 7 to 12, it is permissible in nature. If the chloride concentration is 12 to 20, is doubtful in nature. If the chloride concentration is greater than 20, then it is not safe and it cannot be used for that particular water for the irrigation purpose. If it is 0 to 4 in the irrigation water, then particular water can be used for the irrigation purpose. So here the chloride concentration is designated as it is the ratio of chloride plus nitrates by carbonates plus bicarbonates plus sulfate plus chlorides plus nitrates. Next is the soluble sodium percentage, SSP. All soluble cations will be expressed in milliequivalent per liter in the irrigation water having SSP value of 60 and above, which is considered as harmful in nature. So soluble sodium percentage is the ratio of sodium to the calcium plus magnesium plus sodium. So here the important point is that if SSP value is above 60, then it is harmful to the crops. Next hazard is the magnesium hazard. So magnesium is the important qualitative criteria in judging the irrigation water. So it is the magnesium content in relation to the total divalent cations. The magnesium absorption by the soil affects the physical properties. The magnesium effects on soil when there is calcium is to magnesium declines below 50. Magnesium hazard in the irrigation water is expected when the calcium plus magnesium is more than 1. Here, the magnesium, so magnesium is the hazard when there is more amount of magnesium ions or the calcium ions present in the irrigation water. So when there is more amount of calcium plus magnesium, I mean the ratio of calcium plus magnesium which is below 50, then it causes harmful effect on the plants. The magnesium hazard in irrigation water is calcium is to magnesium is more than 1, then it is good. So the magnesium hazard is designated as it is a ratio between the magnesium to the calcium plus magnesium. Criteria for, so next is the nitrate concentration. So nitrate concentration is nothing but or nitrate toxicity. So when the irrigation water containing more amount of nitrates, I mean the nitrogen present in the nitrates in higher amounts, then there is a problem in giving irrigation water to the crops. Continuous various physical properties will be affected when there is more quantity, when there is more amount of nitrates present in the soil, which affects the plant growth severely. According to the EPA Environmental Protection Act, if the nitrate concentration in irrigation water, that is 10 milligrams, it is a prescribed limit which is used in the drinking water for the human consumption, though it is 4 times more in the livestock. Drinking water, when it is contaminated with the more amount of nitrates, then it causes major health issues in the humans and also animals such as metamoglobemia, which is also known as the blue baby syndrome, or it also causes the carcinogenic effects. So nitrate concentration is one of the hazard which is used for the criteria of irrigation water. So in the nitrate concentration, when such type of water is applied to the crops, it causes poor growth of the crops. The physical properties of the soil, physical properties of the plant is severely affected. According to the EPA, that is the Environmental Protection Act, the prescribed limit in the irrigation water or in the drinking water, the nitrate concentration should be 10 mg per liter, which is used for the human consumption, though it is 4 times more in the livestock. So if the drinking water contains more amount of nitrates, that is above 10 mg per liter, it causes the health issue in the humans and also animals. So the disease is known as the methemoglobinemia, which is also known as the blue baby syndrome, and also causes the carcinogenic effects. So this is the condition of the blue baby syndrome. Here the which is mostly seen in the infant babies. So here the skin color of the baby seems to be in blue color. So this blue color is due to the lack of the oxygen supply in the blood condition. Thereby the color of the skin seems to be in the blue color, and also certain carcinogenic issues that also it also results in the certain heart failures, which is also caused due to this blue baby syndrome. Lack of oxygen in the different veins in the blood, which causes this disease. The baby's skin turns blue color due to the lack of oxygen in their blood. This can be caused by various factors, which include the congenital heart defects or exposed to the nitrate contaminated water. Next is the lithium hazard. Lithium is one of the important trace elements which may be found in most of the saline water or in the irrigated water. It has been found that small concentration of lithium, that is 0.05 to 0.1 ppm of lithium in the irrigation water, produce a very toxic effect on the plant growth, especially in the citrus. So here the important point as per the JRF point of view is the nitrate concentration in the human consumption or in the drinking water is 10 mg per liter. If this concentration is increased, it causes the nitrate concentration in drinking water is increased. It causes the disease known as the methemoglobinemia, which is also known as the blue baby syndrome, or heart failures. Suitability of irrigation water. Suitability of irrigation water, it is determined by 5 factors, which includes SI is equals to, that is suitability of irrigation water equals to F of Q S P C M. Q is the quality of irrigation water. S is the amount of soil to be irrigated. Nature of the crop plants to be grown. C is the climatic condition. M is the management practices. So quality of irrigation water. So in the quality of irrigation water, the amount, the nature and proportion of various cations and anions present in the irrigation water. Nature of soil to be irrigated. So in the nature of soil, the texture, structure, drainage, permeability, depth of water table, chemical composition of soil, pH, EC, calcium carbonate will determine the effect of irrigation water present in the soil. Nature of the crop plants to be grown. The water which may not be suitable for the very sensitive crops or may be excellent for the salt tolerant crops, deals with the nature of crops to be grown. Climatic conditions. So generally these types of saline soils are formed in areas where there is less water and more amount of evaporation and transpiration, which is having the arid and semi-arid conditions. Management practices includes tillage method, irrigation method, or growing application of gypsum or lime in certain saline soils or the sodic soils. Use of saline water. So we can be as the physical condition of saline water is flocculated condition. I mean that is flocculation condition is in the sense there is all the soil particles will be clumped together. That is known as the flocculation condition. So the physical soil structure or the physical condition of saline soils is floculated. That is why we can use saline water for the irrigation purpose. If the soils containing high amount of dissolved salts have the high permeable sandy soils. Similarly, the water showing considerable amount of alkali hazards have also been used successfully on permeable soils or by adding the gypsum or FIM or semi-permeable soils. The high RSC content can be corrected by addition of gypsum and water table, and water can be used for this irrigation purpose. Some of the attempts also made by using saline water. The combination of saline water along with the good quality of irrigation water can also be done by alternate irrigation with good and bad quality of water. The amount of water applied for irrigation needs to be reduced. This is also not possible with most of the wide surface irrigation methods like sprinkler and drip methods. Wastewater supplies not only nutrients but also some of the toxic elements such as the total ions like chlorides, carbonates, bicarbonate, sulfate, sodium, chromium, calcium, magnesium, which are present in the higher concentration. So treatment of wastewater should be done in order to use this saline water for the irrigation purpose. Here, we can use saline water for the irrigation purpose by removing the dissolved salts present in the high permeable sandy soils. So when we remove the dissolved salts, that is by maintaining proper drainage conditions, by removing proper dissolved salts, by maintaining proper drainage conditions, we can maintain the level of salts in this by doing the proper drainage condition. Similarly, when the soils have high amount of alkali hazard or alkali, that is the sodium concentrations of sodium, we can add the gypsum and also FIM on the semi-permeable soils in order to reduce this alkali hazard. RSC content, that is the residual sodium carbonate, can also be corrected. I mean, the sodium which is present in the soil can also be reduced. This hazard can be reclaimed by addition of gypsum, and the water can be used for the irrigation purpose. Some of the attempts like by using the alternate use of good quality of water with bad water, that is the good quality of irrigation water with saline water can also be done alternatively, so that leaching phenomena occurs, thereby salts are removed and we can use saline water for the irrigation purpose. Frequent saline waters, and by use frequent saline waters, the amount of water applied for irrigation needs to be reduced. If we use more amount of saline waters for the irrigation purpose, the amount of irrigation need to be reduced, because the amount of salts which are present in that particular soils, the amount of salts which are present in particular waters can be reduced. So in order to reduce this particular salts in the saline waters, we can use this saline water with the help of the sprinkler or drip methods. So sprinkler or drip method, this is the irrigation method. So with the help, by using this drip method, so only the water is given to the crops whenever it is required. So no wastage of water can be done, and water saving is more in the drip method. So drip method is the more feasible one when we are using the saline water for the irrigation purpose. And also saline water, wastewater when we are using for the irrigation purpose also contains many amount of ions like chlorides, carbonates, bicarbonates, sulfides, sodium, calcium, magnesium, which are present in the higher concentration. So before using this wastewater for the irrigation purpose, treatment of this wastewater should be done so that the amount of salts are removed. Thereby, we can use this particular water with the good quality of water. So first is the alkali hazard. Alkali hazard can be done by the application of gypsum or the FIM. Next is the residual sodium content or RSC hazard can be determined by the addition of gypsum to that particular water and can be used for the irrigation purpose. Next is the alternate use of the saline water and the good quality of irrigation water. Thereby the salts are removed and we can save the water. And also saline water can also be used with the sprinkler or the drip methods. So in the drip method, the use of saline water is more efficient. It is because all the salts in the drip, the only whenever the plants require, the water is given to the crops. Thereby, the presence of salts will be reduced in that particular areas. And also the wastewater, when we use for the irrigation purpose, the treatment should be done. Treatment of wastewater should be done before it is used for the irrigation purpose, so that the salts like chlorides, carbonates, bicarbonates, chromium, calcium, magnesium are removed and we can use for the irrigation purpose. Common problems which are present in the saline water. The common problems include salinity, permeability, toxicity, and miscellaneous. So salinity is nothing but if the quantity of salts in the irrigation water is high, the salts will accumulate. The salts will accumulate in the root zone of the crop. It affects the crop growth and the yield. Excess salt can also reduce the uptake of the water and also the nutrients from the soil solution. So this is known as the salinity condition, which is seen in the saline soils mostly. And also the osmotic pressure, which is created in the saline soils. So this osmotic pressure, which is created between the root zone and also on the soil surface. So between the root surface and the soil solution, this osmotic pressure is created. Thereby, the plant roots have to spend more amount of energy to withdraw or to draw the nutrients from the deeper layers of soil. This is the physiological drought condition where water is available, but plants cannot utilize that moisture for the growth, for its growth. That is known as the osmotic stress, which is also known as physiological drought condition seen in the saline soils. Next is the permeability. So if the saline soils generally contains more amounts of salts. If there are more amount of salts, it reduces the infiltration rate of the soil profile. Toxicity, that is known as a specific ion effect. So when the certain ions or this certain nutrient concentration is higher in the plants, when these ions are accumulated in the larger quantities, it results in the plant toxicity. Some of the other nutrients, like if there is excess nitrogen in the irrigation water, it causes excessive vegetation growth, leads to the lodging, delayed crop maturity, white deposits which are seen on the fruits may also occur due to the sprinkler irrigation with higher bicarbonate water. So first is the salinity hazard. So major problems include the salinity hazard. So in the salinity hazard, the osmotic stress leads to the physiological drought condition, which is exclusively seen in the saline soil. Next is the permeability. So permeability is nothing but the it is related to the infiltration rate or the aeration. So when there is impermeable, because of the more presence of salts, the water is impermeable in nature, and the rate of infiltration is affected in the soil profile. Next is the toxicity. So because of the excess amounts of boron, fluoride, lithium, aluminium, and chloride, the toxicity of these ions increases. Thereby, the death of the crops or it affects the germinations of the plants is severely affected. And if the soils contains excess amount of nitrogen, if the soils contains excess amount of nitrogen present in them, it leads to vegetative growth. So vegetative growth is only continued in the crops if there is the water which is given to the crops containing more amount of nitrogen. And other symptoms like lodging, delayed crop maturity is also seen because of the water containing more amount of nitrogen. And also the white deposits which are seen on the fruits, which is caused due to the sprinkler irrigation with when it contains more amount of bicarbonates present in the water. So what is to be done while we are using this saline water? So what are the measures that we need to take while using this saline water? So first is that we need to determine the salinity hazard. That is the amount of salt which is stored in the soil or in the regolith, or the salts which are present in the water table, or if the salts which are present in the water table should be measured So this can be done by using the salinity assessment, that is the electrical, by measuring the electrical conductivity. Next thing is that we need to determine the source of water and the measure of water for the salinity, purpose regularly. A chemical analysis is to be done and the test like EC, SAR, pH is to be done for the waters before using it to the irrigation purpose. Next is that we need to measure the soil salinity before and during the irrigation. We need to measure the soil salinity before irrigation and during the irrigation of the year. We need to measure at the surface and in the zone just above the clay B horizon. If we are adding salts, the level of these two locations can increase rapidly. Generally, the salts are present in the surface in the zone and above the clay B horizon. If you are adding the salts, the levels of these salts in these particular layers increases rapidly. Improve your drainage condition by means of or by providing the subsurface drainage. So the subsurface drainage will be effective where there is a drainage condition. Ensure that to leach out the salts which are built up by using the additional irrigations and rainfall. And also check out the leaching phenomena should be done in order to leaching and flushing phenomena should be done in order to leach out the salts to the deeper layers of soil. So first we need to measure the salinity hazard which is present in the saline water or the water used for the irrigation purpose. That is known as the salinity assessment. Next, we need to measure the chemical analysis of water is also needed for betterment of the usage of this irrigation water. Measure the soil salinity before and after the irrigation year. Make sure that the surface and in the zone just below the clay B horizon, if you are adding salt in these particular levels, two locations increase the salts rapidly. The maintaining of subsurface drainage is most effective while using this saline water, and also the leaching and flushing of salts is better done in order to leach out the salts to the deeper layers of soil. Maintaining the proper maintaining of calcium and magnesium balance by using gypsum and lime in the appropriate quantities. Application of greater amounts of organic matter such as FIM compost to the soil in order to improve the permeable nature and also the soil structural conditions. Mixing good quality of water with the poor water in the irrigation purpose in the proper proportions can also be effective while using this saline water for the irrigation purpose. Periodical application of or incorporation of green manures in the crops in the soil can also be effective. Raising of salt-tolerant crops like cotton, ragi, sugar beet, paddy, groundnut, and sorghum, tobacco, onion, amaranthus, and lucerne is also effective where the saline water can be used for the irrigation purpose. So here, in order to maintain the calcium and gypsum balance, proper maintenance of calcium and gypsum balance, we need to apply the lime and the gypsum in the appropriate limits. We need to apply the proper application of organic matter such as FIM and compost. When we use this FIM and compost, it improves the physical conditions of soil like soil structure, soil permeability and infiltration rate and soil aeration. So mixing of good quality of water with the saline water in a proper proportion so that the salts are removed and it can be used for the irrigation purpose. Periodical application of organic matters and incorporation of green manures in the soil is also effective to leach out the salts from the root surface or from the surface of soil. Raising of salt-tolerant crops like cotton, ragi, sugar beet, and paddy is also effective while using this saline water for the irrigation purpose. Management practices for efficient use of saline water. So the management practices includes blending of water supplies, more frequent irrigation, selection of salt-tolerant crops and salt-tolerant varieties, usage of extra water for the leaching purpose, that is leaching or flushing of salts, conjunctive use of fresh and saline waters, cultural methods which includes subsoiling, chiseling, ploughing, or to break up the hot pans, decreasing the compaction, which improves the water infiltration rate. Special treatments like tillage, deep ploughing, addition or mixing of sand with the soil layer, addition of organic matter, gypsum and lime to improve the permeable nature of soil. Here, the management practices for efficient usage of saline water includes blending of waters. That is the dual mixing of saline water along with the non-saline water. That is known as the blending of water supplies. Thereby, we can use the saline water effectively and we can save the water. More frequent irrigation. So more frequent irrigations, like when we give more amount of irrigation to the particular salt affected soils, so more amount of when more amount of water is given, all the salts which are present in the surface of soils will be leached down to the deeper layers of soil. Thereby, the salts are removed. Selection of salt tolerant crops and salt tolerant varieties, as we have discussed in the previous slide, that is salt tolerant varieties. Usage of extra water for the leaching phenomena. It is the leaching, flushing, and flooding phenomena, which is used exclusively to remove the salts from the surface of soil. Conjunctive use of fresh and saline water, that is the combination of fresh water and the saline waters. Cultural practices include subsoiling, chiseling, ploughing the hot pans, thereby improves the reduces the soil sealing and soil drainage, and the infiltration rate and aeration is improved by breaking the hot pans. Special treatments includes tillage, addition and mixing of sand with the soil layer, addition of organic matter, gypsum, green manures, which is to be done in order to improve the permeability of soil. So here, this is the blending of water supplies. So alternate source of irrigation water which is available. Mixing the two sources may be helpful in obtaining the water which is acceptable for the irrigation. So here, one is the good quality of water and other is the saline water. So blending, mixing of these two waters can be done. So whenever the crop is required. So when we do this blending of waters, we can save the water. Mixing of water with different salinities. So here, so by mixing this good quality of water and with saline water, saline water and non-saline water, which is to be done by the drip irrigation. So in the drip irrigation, so the drippers are fit. So whenever the water is required, then only it is given to the crops. So whatever the salts, when we are giving this particular water with the drip irrigation, of good quality of water. So mixing of saline water and the non-saline water. So by mixing of different types of salinity water, that is the non-saline water and saline water, can be done with the help of the drip irrigation. So in the drip irrigation, the amount of water is given only at a growth stage, when only at a period whenever the crop is required. So in the drippers, the whatever, if the saline water is given or the non-saline water is given in these drippers, all the salts will be accumulated here so that the removal of salts can be done very easily. Thereby we can save the water. More frequent irrigations maintain high soil water contents in the upper parts of the root zone while reducing the concentration of the soluble salts. This results in reducing the effect of high salts on the availability of the crops to the plant, therefore promote the better crop growth. The sprinkler method of irrigation is more amendable with increased frequency of water application. In the surface irrigation methods, more frequent irrigations may be given in order to remove the salts. Here, more frequent irrigations can be done in order to remove the salts. So as the saline soils are most of the salts are present on the surface layers of soil. If we give more frequent irrigations, all the salts which are present on the surface layer will be leached to the below layers or below the root zone, thereby reducing the soluble salt concentration on the surface of soil. And also the sprinkler method of irrigation is generally more adaptable with increased frequency of water application. In surface irrigation, more frequent irrigations may be given in order to reduce the water use. Growing of salt-tolerant crop and salt-tolerant varieties. So, proper choice of crops is more essential in order to earn the good returns when there is high salinity water. Selection and breeding of salt-resistant crop varieties offer a tremendous possibility of using saline waters for the crop production. So here it is an example of sequential saline drainage water use. So saline drainage water can be reused. So salt sensitive trees. So growing of salt sensitive trees and the salt tolerant crops. So by growing these salt tolerant trees and salt resistant trees, so when irrigation, saline drainage water or the saline water is given to these particular crops, the salt water will be percolated to the salt tolerant crops. From the salt tolerant crops, the salt resistant crops which are grown here, the salt resistant crops uptake these salts which are present, and thereby the salts are removed. The salt resistant crops and also the halophytes. Halophytes are nothing but the plants which are grown in the high salt condition. Those are known as the halophytes. So here the salt resistant crops and also halophytes helps in the removal of salts from these helps in removal of salts. So when there is saline drainage water is used when saline drainage water is used for salt sensitive crops and salt tolerant crops, here the salt removal is done by using the salt resistant trees or species and halophytes and solar water pond evaporator. So these three conditions, that is the salt resistant crops, halophytes and solar pond evaporators, helps in removal of salts from the surface layers when we use saline drainage water for the irrigation purpose. Next is the semi-tolerant crops. So in the growth stages of the semi-tolerant crops, sowing, seedling, vegetative growth, flowering, fruit, and the ripening stage. So at the sowing stage and the seedling stage, fresh water can be given. And the vegetative stage, the saline water is given. Flowering and fruiting stage, fresh water plus leaching requirement can be done. And the ripening stage, no irrigation can be done. So in the semi-tolerant crops, the salinity is reduced in this manner. Next is the improving irrigation efficiency and productivity by PRD method. So PRD method is the partial root zone drying method. So in partial root zone drying method is one of the method which is exclusively used for the usage of saline water for the irrigation purpose. So partial root zone drying method. So here the amount of water can be saved by alternate wetting and drying of crops. So on is the or so this is nothing but the on and off method. So that is the alternate wetting and alternate drying. So here once at one time the wetting of crop is done, and it is wetting of crop. After wetting of crop, after some time, then drying is done. So when alternate wetting and drying of crops are done in the root zone areas, particularly when the irrigation water is given in the alternate wetting and drying conditions, the amounts of salts can be reduced. Thereby, the water can be saved because of this partial root zone drying method, which is exclusively used by the usage of this saline water or the drainage water for the irrigation purpose. So partial root zone drying method is one of the techniques used by irrigating half of the plant's root zone surface while the other half is dried. So first half is wetting of root zone is done while the other half is dry. Then other surface, the next wetting is done, then the other half is dry. So because of these alternate wetting and drying, the amount of salts which are present in the root zone is removed. Thereby, the amount of water is also saved because of this partial root zone drying method. So this is done by rotating with wet and dry sides near the root zone, and this process can be achieved through the techniques like drip irrigation. So PRD method, that is the plant root zone drying method, saves water. It saves more amount of water. It also uses the improved water use efficiency. So more amount of water can be used. Reduce transpiration. So transpiration can be reduced. So when there is more, so reduce the transpiration because of the stomatal closing. When there is a reduced transpiration, one of the acid, that is the abscisic acid, that is plant stress hormone, is released in the plant root cells. So when this hormone is released, there is a partial closing of stomata. When there is partial closing of stomata, thereby the transpiration is reduced, where the water is also saved because of this PRD method. Water conservation can be done because of the reduced transpiration. Reduced transpiration, also the reduced chlorophyll activity or the reduced photosynthesis phenomena. Water saving is done when there is less transpiration and less evapotranspiration, less photosynthesis phenomena. Reduced leaching, potential for enhanced quality. The quality of fruits and vegetables can be maintained because of this PRD method. Drip irrigation. Drip irrigation method is most commonly implemented in this PRD for precise control of water delivering to the root zone. Alternate sides of the plant rows, method can be done so that water can be saved, and monitoring the soil moisture. Monitoring soil moisture when there is both wetting and drying conditions can also help in the PRD practices. So PRD saves water. So by improved water use efficiency, reduce the transpiration because of the release of the ABA, that is abscisic acid, thereby reduce the transpiration and also reduced photosynthesis. Next is the water conservation. Water conservation can be done by using this drip irrigation in the PRD method. Water saving. Next is the potential for enhanced quality. So quality of fruits and vegetables can be maintained because of this PRD method. Reduced leaching. Leaching of water is also reduced because of this PRD method. So this is the subsurface and surface of drip irrigation by using this saline waters. So as I said before, the PRD method in the drip irrigation is mostly used. So in the PRD method, partial root zone drying method, this drip is most frequently used because in the drip irrigation, Precise control of water is given to the crop only when crop requires water. Thereby, it conserves or saves most amount of water. Water use efficiency is mostly done by PRD method by using this drip irrigation. Furrow irrigation. So in the furrow irrigation, the plants are grown. So in the furrow irrigation, the plants are grown on the furrows, on the ridges. So plants are grown on the furrows, on the ridges. The saline water can be used for the irrigation purpose, and the salts will be accumulated on the ridges, and very little amounts of salts come on the furrows. Thereby, the growth of plants is good by using this furrow method of irrigation, by using the saline waters. Use of extra water for the leaching purpose, not to prevent the extra salt accumulation in the soil. It is necessary to remove the salts periodically by the application of water in excess amounts for the consumptive use. The excess water which is applied, when we apply excess water, it helps in removal of salts from the root zone, thereby creating the internal drainage. Richard concept determine the leaching requirement. So leaching requirement is nothing but it is a level where the amount of salts which are present on surface of soils will be leached below the deeper layers of soil in order to decrease the salt concentration, thereby creating the proper drainage and proper aeration conditions. In the surface irrigation method, 10 to 20% or more losses due to the deep percolation in water in the light and the medium textured soils can also be done for the leaching requirements in the salinity control. In the heavy textured soils or in the soils having the expanding type of clay minerals, more water is difficult due to the poor permeability and consequent aeration problems. Application of excess water through useful salinity control puts high demand for the water resources. On the other hand, salt load of drainage water on the other hand. Controlling the interval between the irrigations is the most important management practice for obtaining the higher yields in the saline water. So extra water, so leaching phenomena can be done in order to remove the extra salts. So it is by controlling the interval between controlling the application of water intervals between the irrigation, which is controlling the intervals between the irrigation water is the most important management practice for obtaining the better yields. Next is applying excess amount of water in order to reduce the salinity, in order to reduce the salt or leach out the salts from the surface layers to the deeper layers of soil. In the heavy textured soils, I mean in the clay soils there is expanding type of clay, that is 2:1 type of clay, that is smectite, vermiculite. So in that particular soils, when we give this saline water or the saline water for the irrigation purpose, more amount of salts will be accumulated and it creates the drainage and the permeable problems, which causes the poor permeability of soils and the aeration problems. Richard concept, that is the leaching requirement can be done. Leaching requirement is nothing but it is a phenomena where the amount of extra water can be used for flushing or flooding the soil so that the salts will be removed. Thereby, the salt control can be done and salts will be leached out into the deeper layers of soil. That is known as the leaching requirement, which is specifically done in order to remove the excess salts from the surface layers. So if you are doing the leaching requirement, then the salts are removed periodically. Then there is more consumptive use of water. Thereby, the proper internal drainage and aeration conditions is good. Thereby, there is good growth of the crops. So thank you. I hope this video is useful. So if you like my video, do share, subscribe, comment my video. Thank you.